All right, you guys ready?
Yeah, just a moment. Welcome everybody again for the next talk we have in the Majorana-Raychaudhuri seminar series. We have Moritz Münchmeyer from University Wisconsin-Madison, and he's going to talk about explorations between theory and artificial intelligence in cosmology.
All right, guys. Yeah, thank you very much for having me. Um, yeah, I wasn't so sure what the background of the audience was, whether people are more theoretically minded or more like know more about cosmology or more about theory. So I've prepared a bit of a mix of things I've been working on. So I thought in the first part of the talk I'll talk about something that's in my main line of research, which is to figure out how to use machine learning for robust constraints on primordial non-Gaussianity. And then the second part, I'll talk about our new project on reasoning with LLMs. With a paper this week on arXiv was called TP Bench. Maybe some of you have seen it. And I'll present that a little bit. Of course, interrupt me anytime if you have questions, okay? I'll give a bit of I'll give a bit of background first. So I just saw it looks like we have a lot of theorists in here, so I probably don't need to explain too much what non-Gaussian entails. But okay, so this first part of my work is with my grad student Yuri, who's really great. My former postdoc Utkarsh, who is now at Caltech, also as a postdoc, and my collaborator Kendrick at Pyramid Institute. Um, all right, so this is if you're not all theorists of primordial non-Gaussianity, right? It's the matter of figuring out what the correlation functions are, so the endpoint functions from inflation. And the simplest way to do this is called local primordial non-Gaussianity, which comes from which mathematically is defined by squaring the field. That's why it's called local. Um, it turns out it's also happening in inflation models. So multi-field inflation models generate exactly that signature. And sort of as a theory target, it was said that we want to constrain FNL to be smaller than one, um, to show that or to motivate that it's single field inflation. Well, if it's larger than one, it pretty much means that it has to be multi-field inflation. And the current constraint is FNL of sigma FNL of about 5. So we'd like to go about 10 times tighter to hit this bound. I should be, of course, honest that this bound isn't a very sharp bound, right? This is something, it's more of a orientation. And right, the parameter FNL, so if FNL were something like 100,000 or 10,000 to 100,000, then the field would be as Gaussian as it is non-Gaussian. And so we're already constraining it pretty well. So FNL is already constrained to be like 1 in 10,000 the power of Gaussian. All right. Longer term, of course, we would like to detect masses, couplings, and spins of primordial fields. And there's also the squeeze limit. It's also really interesting for that. And here we're going to work particularly on non-Gaussianity in the squeeze limit. So if you do, so I like primordial physics and I like machine learning. And if you wanted to, so if you did sort of a naive approach to learn to extract primordial non-Gaussianity, and approach is naive, but it doesn't mean people aren't trying it. So you would just make a lot of simulations with different values of FML, and then you would just put them in a CNN, and you would check what you would try to do supervised learning and get FNL in that way. And this would, of course, work with any non-Gaussianity in principle. You just hope that the neural network is able to pick up the signatures in the data. So, unfortunately, this method doesn't really work in practice. And that is because non-Gaussianities are really small signal, and so it's already constrained from Planck to be really small, and um, the contributions from non-linearities are really large, right? So the non dynamics of gravitation makes really large endpoint functions, and in particular, baryonic uncertainty will change the cosmic web a little bit, as will sort of UV dark matter physics if you want. by which I mean that the scales that you are integrating out in the EFTF logical structure. And so we wanted to find a method that would work well in practice, rather than only on simulations. And so indeed that's possible. So to explain how this works, let me first give you a sort of, sorry, do you have a question? I heard
Um,
something, but
no, I don't think so. Maybe some noise, maybe.
okay. All right. So let's do something simpler at first. Instead of trying to measure non-Gaussianity, we would just want to measure sigma 8, right? So you guys know sigma 8 is the amplitude of it's basically AS measured later in the cosmos. So it is the amplitude of the linear fluctuation amplitude of the matter field. And people have known by now that you can use a neural network to measure AS really precisely in simulations. And so people sometimes will tell you, I've trained this new, the CNN or graph neural network or anything, and tell them that it's amazing at measuring sigma 8 or measuring omega m. And it's true that they are very good at that. The problem is, however, that the simulations are not trustworthy. Things get even worse when we want to do the halo. So if we don't have the matter field, in reality, we are seeing galaxies, and we just like to approximate galaxies as dark matter halos. And so the next step that people do, they train their neural network on dark matter halos, to extract something. And so if we would train a neural network on the dark matter halos to measure sigma 8, this would also give you a really good constraint, but unfortunately, it wouldn't be trustworthy. So as a practical example, if you did a camel simulations, and the camel simulations are being run with different subgrid models. So for example, with with Illustris and Simba. And so if you run the same initial conditions with two different camels codes, then the number of galaxies you will get in the two different volumes that you ran with two different codes is different by 30%. So the baryonic uncertainty is so large that you get a 30% different number of galaxies in the two volumes. And so sigma 8 is already measured near percent level with perturbative cosmic scales, right? And so if you have an observable that's 30% systematic uncertainty is 30%, but you already measured the thing you want to measure from other scales to percent level uncertainty, it's clear that this method is useless. And so when people use CNNs to measure sigma 8 or so, then from small scales, then you basically don't need to pay attention. So, however, in our case, where I think our method is interesting, the situation is different. So we are going to use the scale-dependent bias. I don't know to what extent people know what scale-dependent bias is so far here in your group, depending on how much you theorists, some more observers. The scale-dependent bias, now I'm going to, sorry? No? Okay. So I'm going to back from neural networks, I go now to scale-dependent bias. So this topic, scale-dependent bias by itself has nothing to do with neural networks, but we're going to combine scale-dependent bias with neural networks then. So let me recall what scale-dependent bias is. So this is this effect that the galaxy power spectrum on large scales gets this kink. So the halo or galaxy power spectrum, it has this 1 over k square dependence on FNL on large scales, which was a really the guy who found this first in simulation was Neil Dalal. And to my knowledge, this was a big result by now, almost 20 years ago. And it came really as a surprise to people because they had not expected this. Once you know it, it's clear in the theory where it comes from, but it was something that people discovered in simulations. And so you get this kink on large scales where the power spectrum turns around suddenly if F and L is non-zero. And so this is called scale-dependent bias. Note that it only happens for the galaxy field, not for the matter field. This is something theorists often get very confused about. So this effect comes due to nonlinear physics. So it's not in the matter power spectrum. If you make a simulation with FNL and you're only looking at the metapower spectrum, then it will not have this feature. In fact, the loop corrections due to FNLs in the metapower spectrum are really small. All right. So our idea for this project was, so a scale-dependent bias is robust to baryonic physics because you can marginalize over the bias parameter that incorporates this method. And our idea was whether we could make a neural network method that would have the same property as scale-dependent bias, so one that would also allow you to marginalize over baryonic uncertainty. So, and to understand how our method works, you have to recall what nonlinear. You have to recall a little bit how this local non-Gaussianity, what it actually does. So local non-Gaussianity, if you take the if you calculate the like you go to momentum space and you stare at the equation, then you'll see that local non-Gaussianity is a large-scale modulation of small-scale power. So that means that in different parts of the sky, you have more or less small-scale power, depending on whether the long mode is large or small at that point. So normally in a Gaussian random field, right, the modes are uncorrelated. So in a Gaussian random field, the small-scale modes and large-scale modes are uncorrelated. But if you make F and L large, then this will lead to, on small scales, it will lead to scales where the large mode is large, it will give you a large amplitude, and where the large mode is small, it will give you a small amplitude. And this means that sort of the large scale field is modulating the local sigma 8. So you could think of it as, if you're here on the slide, if you're living in the blue region, then your sigma 8 that you are going to measure from data from the blue region will be larger than a guy would measure that lives in the red region, and he would measure a lower sigma 8. And so scale-dependent bias is working because the galaxy number density is sensitive to the local power. So basically the galaxy number density so galaxies basically form when the density goes over some critical threshold, and because of that, the galaxy number density is sensitive to the local sigma 8. And so our idea basically was the following, that if normal scale-dependent bias that works in practice to measure FNL, if that depends on the galaxy number density, which measures local sigma 8, then if we could find something else that measures local sigma 8 better than the galaxy number density, some other nonlinear function, then this would give us better constraints. And this is the idea. And of course, we're going to use a neural network for that. So the way how the method works here is that in terms of machine learning technology, it's very simple. It just uses a CNN, but the way how the CNN is used is sort of clever. So the CNN is trained to measure local sigma 8 on the sky. So this map that you see here, right, the red box would be measuring what on this previous plot here that was the blue or the red small scale power. So it scans over the sky to measure local sigma 8. And normally, in normal scale-dependent bias, it would be we would do this, make sort of the same sigma 8 map by halo counting. But here we're using a neural network. In this case here, it gets to see the meta density. I'll talk later about when the neural network looks at the halo density. But here, so this is here at this level, it's sort of simulation work where the neural network is getting the meta density. And so our prediction was that if we train a neural network to measure local sigma 8, then that this field must also, in an FNL cosmology, must also have scale-dependent bias. So we trained this neural network and then we applied it to simulations that have FNL in them. For example, the Quixote simulations. And sort of our model that we expected to see was that that any field that is sensitive to local sigma 8, such as a neural network, would also have the bias model of scale-dependent bias. So we should get So here delta pi would be the output of the neural network field, which was in the old scale dependent bias was the output of the halo field. So here now this is the neural network field, and the neural network field will also have a Gaussian bias, which is the normal like galaxy linear bias that you know about. And the second one would be the so-called non-Gaussian bias, which is how basically how the field reacts to sigma 8. And so this was our analytic model. And so when we trained the neural network, we did this sort of analysis, and we were very pleased to find that indeed the neural network behaves exactly as we predicted. So this is one example here. So here with large FNL, of course, we know that FNL is not 250. This is sort of to make the effect very clear and to show that there's no bias even at even if you have a large large FNL effect. And so you can see now that our pi field here, we took the power spectrum and went to a large scale. So here k is on the x-axis, right? So, and you see that on these large scales where k is 10 to the minus 2 or 10 to the minus 3, this effect gets pretty big. And you also see that if we have in a simulation without FNL, such as the green curve, or the dotted red curve, you see that the field is that this field is flat. And so our method works by first doing this neural network transformation and then looking whether there is or isn't such a kink in the data. And the amplitude of this K2 square kink we can marginalize over. And this is what gives us robustness to baryonic physics. At the bottom you see the noise. We also conjectured that the field should have a flat noise power spectrum, and this is also the case. Okay, so we got on simulations of the matter field, we got that the method works sort of amazingly well. So if you could observe in the universe the matter field, then by this method we could tighten FNL error bars by order a factor of 5. If you compare the black simulation, which has used the matter field plus the halo field, you get sigma FNL of 50. While with ours, you get sigma FNL of 10. And they are both unbiased, so they both have the right value, and both of these methods would work in practice. Both of those are equally sensitive to baryonic physics, right? So the original non-machine learning scale-dependent bias was also sensitive to it was also depends on galaxy formation, which, as I said, has a large systematic bias. But nevertheless, this method works due to the specific analytic property. Okay, so that's what sort of this method. The parts I just showed you are already 2 years old or so. But then in December we had a new paper about this where we worked further on this method. So I think the method is very promising, and it could be the first time that machine learning is actually used to tighten non-Gaussianity constraints in a reliable way on data. So here however, because our previous work was using the meta distribution, which, as you know, is not observable, so now we worked on the halo distribution with the abacus simulations, and the halo distribution looks way more dotty, right? So for people who are more theorists, it looks like that when you see here in this field, and it's clear that the halo distribution won't have as much information as the meta field. So to do this, we had to sort of upgrade our formalism. I didn't want to spend time to go through the math, but we were able to show some properties. So in particular, we were able to prove that there's an optimal way to use the neural networks for the scale dependent bias analysis by training 2 different neural networks. One of the neural networks would be measuring sigma 8, which is what we already have. And the other neural network would be measuring the local matter field, which, as I just said, is not observable. It's the halo field that's observable. And reconstructing the matter field from the halo field in large scale is equivalent to lowering shot noise. So basically, the neural network is trained to reduce shot noise as much as possible. Okay, and so yeah, we could prove that this is optimal. We also sort of showed what optimal loss functions for this are. So we can derive what the optimal loss functions are that will give you in the end fields with minimal possible error. And so this is kind of for cosmology neural network standards. This is a nice analytic work. Usually people just throw you know, train supervised simulations. But here we have some mathematical control of what we should be doing, what is the right loss function, and how optimal can our results get. Okay, so then we applied this to the abacus simulations. Even doing a proper FNL analysis, so there's no abacus with FNL, but even there, a proper FNL analysis with mass-spin halos hadn't really been done, or at least not published. And so on this plot first, we see the analyses, the analyses on abacus without the neural network method, and then afterwards you go to the neural network method. So here you can see that so abacus is a pretty decent volume. I think it's 2 gigaparsec side length. So 8 gigaparsec cubed volume, which is still, however, less than a large survey. So a large survey might still have could still have a couple of times that if it's very large. But it's the closest sort of to it's the closest to a real galaxy survey, a real sized galaxy survey in terms of simulations that we have. And so you can see with this, you would get FNL of order a few, which is this. So the curves as they are on this plot here would already beat Planck by a little bit. But so beating Planck unfortunately is really hard, right? This is why people work so hard on trying to do better large-scale structure analysis, because the Planck results are already really tight. So with DESI, it should be possible to go be better than Planck in practice. And so maybe with our method, even better than it was otherwise possible. And so right, so now we're doing so when we train on halos here, then we get halo features. So a neural network now gets to see the halo position, the halo mass, the halo concentration, which is something that is about how strong the slope is of the halo, of the dark matter distribution, and gets these properties. And if we use those, then we can our neural network can improve significantly over the old scale-dependent bias halo method. However, so I should say that concentration is not so easily observable, and is in principle observable, but it's not. Our model here is not very realistic yet. So we went one step further in realism, but not yet to the far enough to make really a forecast for upcoming experiments. But so if we do that, then we can show here in the plot on the bottom, you can see that again it's possible to make the FNL constraints significantly tighter by a factor of a few with our method. And in fact, so in fact, this is not even the best our method in principle could do. So here we use the CNN, but for a point cloud, in principle, it would be better to use a graph neural network, and we've been working on that too, using a graph neural network. Here you see an example of a graph from a camel simulation. So that would be a graph neural network that looks at the local galaxy distribution. And with the graph neural network, our method would work again the same and would measure local sigma 8, and then we would take this power spectrum and we would see this kink on large scales, and that then we can from which we can make an FNL measurement through a normal Monte Carlo method, then, as you can see here on the blue plot. Okay, so the graph neural network work is still unpublished and not finished. But in principle, it looks that with the graph neural network, you can outperform the previous method even a little bit further and maybe get another factor of 2 or so. But yeah, so we'll see. It's not yet possible to to give really a forecast for DESI or so, what we could do with our method LSD. But I'm hopeful that we can get actual real improvements that will be significant enough to be worth doing. So in conclusion, we developed a new formalism that uses machine learning to probe squeezed limit non-Gaussianity. I presented this for FNL, but it would work for any squeezed limit observable. We compressed the field into neural networks, and we gave a proof that FNL is optimally reconstructed, and we're currently sort of working out these details. All right, I'm going to pause for questions, and then the rest of my time, of which there seems to be still 20 minutes, I'll do this. Okay. Yeah. Excuse me, I didn't hear you. Was there any questions? Okay. If there are no questions, I'm going to talk about something that I'm currently really excited about. Okay. All right, guys. So I'm going to present something else for the rest of my time, which maybe is more interesting for people who are more formally minded. So so I was working with some computer scientists and some physicists. I don't know if you do inflation theory, you might know Dan Chang. We worked on this paper here, which came out this week. It's called TP Bench, a data set and study of AI reasoning capabilities in theoretical physics. So you've all heard probably that AI is becoming I'm sure you're using it yourself for some to ask physics questions, but there has not been so far an evaluation of how well these models work for theoretical physics. There's been quite a bit of work on math, which I'm gonna quickly recall. So this here, for example, is just from this week. So this is a website that tests models on Amy. Amy is a sort of a high school or undergraduate level math competition. So the problems are sort of student level competition problems. And you can see that GPT-4 could solve only 13% of those. And GPT-4, right, is not even a year old. And now O3 Many High can solve 93% of these problems. The progress has been absolutely crazy. And then there was a paper in the fall last year that was called Frontier Math, a benchmark for evaluating advanced mathematical reasoning in AI. We got some really good press. We got some comments, from famous mathematicians about the difficulty of these problems. And so this is a data set that has only really difficult problems on it. So it's much, much harder than Amy to solve, much harder than the previous one. And at the time when the thing came out, AI models could solve under 2% of these problems. And that was in December or so. Now it might be in November or so. And so nowadays, even just 3 months later, here this is the results from the O models, which so you can see that O3 Mini now does already 10% of it before. And if it gets to try 8 times, can even do 20%. And if you read the caption below, if they allow it to use a Python tool, then it apparently can even do 32% of these problems. And so these are research level problems, at least most of them. And so it's clear that this will have impact on theoretical physics. But all of this work was work on mathematics. And so the goal of our paper was to try the same for theoretical physics. So we wanted to make a benchmark but it is smaller than Frontier Math, which has a lot of people, but it's still large enough our benchmark to probe progress on real to probe real progress and see whether they can do research level problems. And so we want to see how well this works and what are sort of common failure modes. And this is what this paper is about. So first, a few comments on differences between mathematical reasoning and physics. So in math and physics, right? We both do math, but it is stylistically pretty different. So math has a very rigid framework, right, where everything gets where things are proved with full logical rigor. Where in physics, usually we do sort of a softer reasoning, where some details are getting left out, and we kind of hope that they won't matter. But it's not always mathematically totally clear when things do converge and how large the error is and so on. And so in other things in theoretical physics, we often sort of calculate things directly, and we have less this proof theorem and proof system of mathematics. We do more derivations rather than sort of inductions and things like that. And so reasoning is somewhat different, and so I think it's really interesting to see how good these models do in physics. So we wanted to make a data set with the following properties. We wanted the problem to be well posed, we wanted it to be original, and we wanted the answer to be auto-verifiable. That means auto-verifiable is that if you have the problem and the computer gives you an answer, that you can write a software code that checks whether the answer was correct, rather than needing a human who checks whether the answer is correct. And we wanted problems where it's not possible to guess the answer or remember it from the literature. The common criticism of these models is that they might just remember everything from their training and they can't actually think at all. So we made new problems there for which you could not Google the answer to them, even if you were super good at Googling. Okay, so here's the properties of our data set. It's pretty small, but it's large enough to give interesting results. So we had problems in different difficulty levels to check how progress evolves with different models. So we had 2 levels of undergraduate problems, 2 levels of grad problems, and research problems. And we had the domains, since we are mostly cosmologists and high energy theorists, these are sort of the domains of our problems, because it would be interesting to add also, say, condensed matter physics or so. And right, then one thing we had to work out is how to do this auto verification. It works similar to the way code competitions work. I don't know if some of you have done code competitions. This is something, if you want to get in computer science, you might try to do lead code or something. And so in these competitions, you need automatic checks whether the answer is correct. And we did sort of the same. I'm going to show you how this works on a very simple problem, but our problems are much harder than that. I'm going to show you the real problems in a minute too. So this here is just about the auto verification. This would be a pretty simple one here. So there's a problem statement which it's about Compton scattering, and the model has to calculate this, and then it has to translate it into a function. And then when we have a function, a Python function, then we can execute it and sample some values and check whether the function is identical to the function we know to be true. The advantage of this is if you just gave it the algebraic expression, then this would not be invariant under, equivalence classes. You can write mathematical expressions in different ways, and the model might not notice whether or not its answer is actually correct. This works well for algebraic expressions, but it's more difficult with integrals and derivatives. All right, so these are the results that we got, and I was personally shocked over the progress of this report that the models got better this quickly. So we started this last summer, and as you can see, our level 4 and level 5 problems last summer GPT-4 over standard, and it could do absolutely nothing. And so we wrote many of these easier problems. We wrote what we now call easy grad level problems to give the model something to chew on. And then the new models in the last 6 months have really crushed the benchmarks. And now graduate level, they can do 50% of our graduate problems. And they're hard. I'll show you some in a minute. And for research problems, still we got about 18% of the problems are correct. So that means that it can, or one can, or three can solve research problems, some research problems that are relevant for us. Now, by research problems, I should say, I don't mean entire publications. So this would not be the amount of work that goes into an entire publication. By research problems, we need sort of mathematical calculations that would be part of a research paper. Perhaps something like you would put in an appendix or something of that sort. I'll show you some examples. Okay, so progress has been really, really fast, also in theoretical physics, and we have some computer scientists which are now interested in testing their models with our new benchmark. However, real reasoning problems that do depend on long mathematical calculations are still mostly unsolved. So among these research problems that were solved, the ones that could be solved were sort of not very long calculations. They were still hard. So it solved one that it took a grad student of mine about 3 days to work out. Um, but like a hard long PFT calculation is still slightly out of range, but not by that much anymore. And we provide in our paper, we provide sort of an error analysis. Okay, let me show you some example problems quickly. To give you an idea. So if you go on our website, you can look at the model results. So, okay, let's start with, I'm just going to show you one of the hard ones, a research problem. This is a problem that comes from Dan Chung. It has something to do with gravitational particle production. It looks like that here. And you're supposed, basically you're calculating the Bogoliubov coefficient. You can hear, I mean, here, it's a quantum field theory calculation in curved spacetime. And so the answer, I'm going to show you what the answer is by Dan Chung here. So there's some contour integral, you have to look some poles and the answer is a pretty lengthy calculation. And the answer is this expression here. So it's a hard problem. And um so the goal was to ask models to solve this. And this problem they cannot just Google. So this is why it's a real test. And models were not currently able to solve this problem here. So I can show you, here you can look, okay, Meta Llama, let's look at the solution from a good model, let's say O3 mini, let's go more towards the end here. So this is now 500 pages of model solutions so that we partially investigated. And this is let's look at okay, these are all okay, here's an O3 minute solution. So it does pretty reasonable stuff, locating the dominant pole, linearizing near the boundary, and so on. It does stuff that's pretty reasonable. And you get something here. This final expression is wrong. So this problem was never cracked by any of the models. However, it's if you go one level below, so for example, this here is something about vacuum entanglement here, and then this here was something to do with calculating the entropy. In this model here, where the answer is also pretty lengthy, the answers of that sort here, and this was cracked by models. Now it is true that this calculation, there are research papers that do sort of the same calculation, though in a somewhat different language, but still it's something that so previously models were absolutely incapable of doing. And now, okay, so here it actually gets the right answer. You see the final answer looks very different than what we saw in the model, in the expert solution, but it does reduce to the same answer, which we check algorithmically until you can see the auto verifier says correct. And here, so you can look through all these problems. So we made 10 problems public. We have 58 problems. The reason we don't make all of them public is that then they will go into training data and then they would be kind of useless. So you need problems that are, you need to keep some problems private so that models and people cannot just train on them to know the answer. And yeah, I was personally really impressed by how well these models are currently working. And so now we're working with some computer scientists so first a few comments on why they are so strong. So I think that it is true that models, so we did summarize it as follows. In summary, current models performance perhaps resembles a student with superhuman literature knowledge, but low intellectual rigor and technical expertise. But low meaning here still, still like a beginning grad student or so. So it's not, they do reasoning. They're not just remembering. But they do have superhuman literature memory. But I wouldn't say that's cheating. Like every human who does research uses as much literature they can. And so it's just a skill they're very good at, but it is not cheating to use literature. if you can. And they're really good at recognizing relevant literature. So we wrote problems in a way that it's not obvious what the relevant literature would be. And they also modified little things, adding some term or something. And models, the top models now are really good at making these little adaptations. So they are not fooled by if you change, an A to an A square or something, or a 5 to a 6, you will fool the model. The newest models you will not normally. Okay, so this was sort of just a benchmark, but of course I'm a scientist and I want to improve these things. I want to contribute to making these things better. So first of all, making good training data is really something, and training and test data is really something where you need experts. The computer scientists can't do it, and they cannot just, look it up. If you look up a problem from Pascal and Schroeder, then of course it has been solved many times and it will be all over the training data. So this is one thing. We're also happy to like if people want to collaborate and contribute problems, we're happy to collaborate. There's some challenges. So automatic verification, for example, is really hard to do if you have integrals and even derivatives, because you can rewrite expressions in different ways. And if they're not algebraic in nature, but they have, as I said, they have more advanced mathematical concepts, then it's hard to write a code that can answer with definitively whether the solution was correct. So that's something we're working on. And then in terms of just improving these methods, there's a lot of, I know how much some of you have followed this. There are various methods from reinforcement learning. And for example, tools currently are not good at using Python, let alone Mathematica. So having training models to interact better with symbolic solvers would be very exciting. And finally, of course, our problems are all in the format of problem and answer, and setting up some kind of benchmark that's more open-ended, more like real research. Right? In real research, you kind of just try to find something interesting, but it's not a problem and answer setup. It would be really interesting to sort of try to set up use cases and evaluate those. And the computer scientists are really interested in that, right? So the computer scientists, they have these super powerful models, but they don't know physics or math and sufficient expert level to sort of compete with their own models. And so they're very interested in seeing what experts in the field can do with that. And yeah, I'm really excited about trying to make these things better, and we have some ideas with computer scientists. Okay, I think that was all my time. If you have any